Okay, and we'll talk about exclusive processes, and I'll introduce you to generalized Parton distributions, or GPDs in short. I'll briefly touch upon the global analysis for GPDs. Okay, so here is the outline. For the first part, I will make a transition from the inclusive processes, which we talked about Wednesday, to exclusive processes. I'll tell you what the difference is, especially in terms of their factorization and what they are giving us. And then that will lead us to the generalized Parton distributions as a product of factorization for exclusive processes. And then I'll only briefly talk about GPDs, and I'll directly move on to the phenomenology of GPDs. And there you'll find that extracting GPDs from experiments is way more difficult than extracting the PDFs. And so that is a problem that we call inverse problem, and that's closely related to the global analysis for GPDs. So let's start with the first part. Let's first recall what we have seen on Wednesday. On Wednesday, I introduced you to the factorization for DIS, or deep inelastic scattering. And there was actually some assumptions. I was oversimplifying the concepts of factorization. And one of the assumption is, so for this leading order diagram and for this one loop diagram, I was telling you that we treat the upper parts that involve this red quark line and here as hot parts. But why are we able to do that? If you think more, you notice that this quark line and this quark line, they are cut by this cut line, which means these quarks are on shell. On shell means their virtuality is 0. So why were we still able to say that they are hard? And then we make approximations for factorizations to carry on. And we can think this more by looking at the space-time diagram, how this process occurs in this. So here, the horizontal direction is z direction, and vertical direction is the time direction. And that's the normal Minkowski space. And here, those two axes are omitted, and they are transformed to the so-called x plus and x minus, which are the light front coordinates. And the x plus and x minus are the two light cones, one along z, one along minus z direction. So recall our assumptions or kinematics on Wednesday. We were having this momentum p that moves along z direction being light-like, which means that the target moves along this yellow band. It's moving at the speed of light, and then it's hit by the virtual photon that comes here. And this virtual photon hits the quark, and then the quark absorbs it and moves along the backward direction, which is along the minus light cone direction. And without this gluon, that gives us the first diagram. And with the gluon, that's the second diagram. So from this picture, you notice that the so-called hard line that we were using on Wednesday is actually an on-shell quark that moves at the speed of light along the backward direction. So it's not so obvious that this quark line can be treated as a hard line. By hard line, we normally mean the virtuality is very large, of order q squared. But if you think more based on our physical intuition, you see that although this quark line is on shell and moves at a long distance at the speed of light, it happens actually way after the hard interactions takes place over here. Because the hard interaction happens at the local point, at the short time period. And the long distance effects by this propagation of quarks should not affect the rate of the DIS. And in other words, because we do not observe this quark, it should not affect the cross-section. And that's our physical intuition. And to put that into our physical or mathematical argument, that's something called unitarity argument. And it's hard to understand this, but I'll just give you some idea. And we learned from quantum field theory course that what unitarity means is that if you sum over all possible states that your initial state can translate to, you should get a unity factor because all possibilities should sum up to 1. And that is what unitarity means. And specific to our case of DRS, what we actually have is a quark along with an arbitrary number of gluons go into this hot part and interact with this virtual photon exchanged by the incoming electron. And this hot interaction can produce a lot of collinear quarks or gluons. And then these collinear quarks and gluons move on to trigger a lot of hadronization activities. But those all happen way after this hard interaction. And because we observe nothing in this hadronic activities, we can actually sum over all possibilities. In other words, we can move this cut line, the red line here, we can move it across all possible states here. And that's what we mean by summing over all possible final states. And that will reduce everything happening here and reduce these complex activities to a single hard blob. And that's what we mean that all the lines here can be treated as hard lines. And then this reduces to what we had on Wednesday. We saw that we can make some approximations here, applying wide identities for the gluons, and that will reduce these two factors into two separate factors, one hot part, one collinear part, which gives us the PDF. So that's the story for DRS. And this use of unitarity is closely related to the physical concept of inclusiveness, which is the condition in measuring in the experimental measurements. And this is actually applicable to many other different kinds of processes. And one notable process is the E plus E minus annihilation to hadron cross-section. What this means is you collide an electron and positron beam, and you measure the total cross-section for the producing any hadronic states. But you don't care about what hadrons you are seeing. As long as you see some hadron in the final state, you record this event. And then you sum over all these events, which give us the total cross-section. In terms of Feynman diagrams, what we are having here is the electron-positron collide, which they first analyze into a virtual photon, and then these hard interactions triggers a lot of collinear quark and gluon lines. And these collinear quark lines and gluon lines can exchange soft gluons in all arbitrary ways. And this soft gluons, by the way, is something we did not see on Wednesday, but as long as you have colored particles moving around, they will exchange soft gluons. And soft gluons should be something we take into account in our argument. And then again, similar to the previous case for DRS, because we don't really observe any specific final states, we can move around this cut to sum over all possible final states. And that will reduce the whole thing into a simple factor of quark production multiplied by its conjugate. And all the activities of collinear and soft gluon exchanges are canceled. And that's a result of unitarity. In a physical language, what we are doing is we notice that all the collinear and soft gluons are associated with long distance and long time activities, and they happen way after the short distance hard interaction takes place. So whatever they do, they should not affect the cross sections, and the cross section is already determined when this hard interaction happens. That's why after summing over all final states, we get a reduced simple cross-section. So in this way, we get that the total cross-section for E plus and minus 2 hadrons is equal to the total cross-section for E plus and minus 2 partons. But this is an approximation, and it's up to corrections suppressed by the large-scale Q. And now we can generalize this a little bit and ask, what if we really observe some hadron in the final state? Suppose you see a pion, and you require there is a pion in the final state with a certain momentum. And that's given by this line here. I denote it as the H for the hadron name and pH for the hadron momentum. And because you observe this hadron, there is some tricky thing because you are no longer able to say that, well, because I observe nothing, I can sum over the final states. Now we explicitly observe this hadron, so we are not able to do that anymore. But we can still apply the same argument by first factorizing the collinear subgraphs and the soft gluons, and they are still factorized in this way. And then after this, you'll see that the first jet factor associated with this observed hadron becomes independent of the other ones. So we are still able to sum over the states for all the other factors, and that still reduce all the other factors to identity. And in the end, we are no longer able to say that every final state effects are canceled, but because we explicitly observe this final state hadron H, and the long distance effect associated with this hadron will remain, and it's there in the so-called fragmentation function. And the factorization in the end is given by the similar Hart coefficient that produces the partons, followed by the fragmentation of the parton into the hadrons. And that's what we get for the fragmentation function. And this is for the E plus and minus collisions. And the same story applies to the hadron inclusive productions for electron-proton collisions. And this is similar to DRS, except that we have an explicit hadron observed here. And the factorization argument applies very similarly to the E plus and minus annihilation case. And in the end, we can still obtain this factorization formula. The long distance effect happens in two places. First, it happens for the incoming proton. And second, it happens for the production of this hadron in the final state. And they both get factorized from the hot part and from each other. And the initial state gives us the PDF, and final state gives us the fragmentation function. And the Hart coefficient is still the scattering of on-shell quark or on-shell gluon with the producing on-shell parton that fragments. So that's the generic feature for inclusive processes. We have seen that for inclusive processes, there are some complications when we want to do the factorization. But the key point physically is that we are breaking the protons, or we are breaking any kind of hadrons. Specifically for the electron scattering, when you hit the electron very hard, you only probe one parton inside the proton, and that breaks the proton in a very hard way. And because we know the colors in QCD are very, very strongly interacted, so once you hit one parton out, there is a strong activity for the gluon exchange among all these colored particles. So this is very theoretically very difficult to handle, and also experimentally, it's also very difficult to handle because you produce a lot of hadrons. But the key point is we do inclusive process. We measure something we want to measure, but we inclusively sum over everything else. By that, we are able to apply the unitarity argument theoretically to show that things still factorize in the way we want. And at the same time, you may be wondering, well, I can select certain events where the hadron does not break. And a simplest example is given here. Suppose we are looking at the electron scattering with the pi zero, although we have no pi zero target, but we can always discuss this theoretically. So suppose you have this kind of scattering, and this pi zero interact with this virtual photon from the electron to produce another real photon. So this is a 2-to-2 process. And in this case, there is no hadron that's broken. And we should not see the crazy soft gluon exchange activity that we have here. And on the other hand, if this interaction happens in a hard way, which means there is a hard momentum transfer here, which can be required by the electron final state electron selection criterion. You require the final state electron to have a large transverse momentum, which will dictate this blob to be a hard interaction. And in that case, you know that because this hard interaction happens at a local point, it should be seeing the parton inside the pion instead of the parton overall as a single particle. And then the dominant partonic configuration is given by this two-parton interaction picture. And by having two partons is because the pion is color neutral. At least we need to have two partons entering this hard blob. So that's a key difference between the so-called exclusive process in which we measure everything we can from the inclusive process, because on the left-hand side, you have only one parton participating in the hard interaction. But here, we have to have at least two partons. And we can slightly generalize this kind of process because we can call the previous one a large angle scattering, because a 2-to-2 scattering with a large PT for the electron dictates the scattering configuration to be large angle 2-to-2. And now we can require that the incoming hadron, say a proton, is not completely annihilated in this hard blob, but it's slightly bent along its momentum direction. Say this electron exchange a hard photon with a proton, but the proton remains intact. It's just giving you a real photon in the final state. And in this case, we are not breaking the hadron, but we still have the proton in the final state. And because we still have a hard interaction, and this hard interaction must be connected to the proton transition via these two parton lines. And we call this process a diffractive scattering. And again, we have at least two parton lines, and having two parton lines means that in reality, the magnitude of this amplitude will be much smaller than the amplitude for inclusive process. So in reality, in a real experiment, these exclusive processes are more rare, and that makes the study for exclusive processes more challenging. So that's an overall feature for these two lectures. Exclusive processes are much less well studied than inclusive processes. A key issue is because we have less statistics in experiments. So you should treat what I'm going to tell you today with more caution because they are less well established. Although this has been studied for almost the same period of time. And let's now look into the exclusive process first for the large angle 2-to-2 hadron scattering. Let's think about this kind of scattering. I have a meson, another meson that collide with each other to produce two other mesons. Because I want to have a hard interaction in order to make perturbative QCD possibly applicable, we should have a hard scale, and the hard scale has to come from the large transverse momentum from the final state to mesons. And in this case, you know that the leading order has to require 2 partons from each incoming hadron and each final state hadron. So that's the lowest order configuration. But as you know, whenever we have partons, we can exchange soft gluons, and soft gluons are always there. So now, compared to the inclusive processes, we know that soft gluons are always a challenge for factorization. And in inclusive processes, we were able to get rid of soft gluons by using the inclusiveness. But now we are looking at everything at the amplitude level with specified initial and final states. We are no longer able to use the sum over final states argument. So how does the gluon still cancel? And that's the key difference between exclusive processes and inclusive processes. And the key is to note that for exclusive processes, each meson has to be connected to the hard blob via 2 collinear parton lines. And these 2 collinear parton lines are so closely to each other because they have to enter together at the same local hard vertex, which means they behave almost like a color neutral pair. And that means the soft gluons should not be able to see them because they are almost color neutral. And therefore, by using the color neutrality, we are able to show that the soft gluons are canceled because essentially soft gluons don't see them. And then all these different mesons become independent of each other, and they get factorized from each other and from the hard part. And that leads to the exclusive process factorization. And what we get for each meson, either in the initial state or in the final state, is something called meson distribution amplitude, or some people shorten this as DA. This can be shown by this diagram. For example, you have a pion, a pi plus. Pi plus turns into a U and D bar quark, and you get nothing. You completely annihilate this pion into U and D bar. That's what this DA is giving. And similarly to the PDF, it has operator definition. The operator inside here is almost the same as the operator for PDF. The difference is, first, we have the pion state that's sitting here and the vacuum state sitting here. Well, in the PDF case, we have the same proton states on both initial and final state here. And the second difference is we have different parton flavors. Here we have a U quark, we have a D quark. That's given by the flavor quantum number. And besides that, it's the same as the PDF, and it's still sitting on the line cone. These 2 fields are separated from each other and connected by a Wilson line. Wilson line guarantees the gauge invariance. And physically, another difference from the inclusive process or PDF is that everything here happens at amplitude level. So this DA is an amplitude object, and therefore it's not related to a cross section. It's related to an amplitude, and or you can call it a light cone wave function, and that's a key feature distinct from the PDF. And now let's move on from the large angle 2-to-2 scattering to the diffractive scattering. And here, the difference is if you just hide this H prime, everything is the same as the previous slide, but now we require this hadron, H is not completely annihilated. It's going from its original direction to a slightly bent direction, but still in the forward direction. And in this case, it's a 2-to-3 process. And you know that we are having almost the same story. The hadron transition is exchanging two partons with the hard interactions here. And these two partons behave almost the same as the two partons here. And soft gluons cancel in the same way. But there is an additional complication, which is because you have a final state hadron connected to this blob, these two partons don't necessarily have to move in the forward direction. It can be that one parton enters the hard interaction and then comes out to merge with the beam remnant to form this diffracted hadron. And this can also happen. And this we distinguish these two regions by calling the first one the ERBL region, and the second one the GLAP region. These four letters refer to four people's names, and that's not so important. And for the GLAP region, we are familiar with this name, and this is because we call it the GLAP is because it's similar to the configuration in the PDF case, except that there you have a cut. Now you don't have that cut. And the factorization happens in a slightly tricky way for the deglap region because we have a color source in this F blob here. But the key is, again, we note that for all the other three hadrons, B, C, and D, their parton pair behave like color neutral objects. So soft gluons don't see all partons from those three mesons. And then the soft gluons essentially only couple to the incoming, the diffracted hadron part. And this can be grouped together into the same object. And that object is then factorized from the hard blob. And we call this one the generalized parton distributions. And this is factorized and convolutes with the hard part. It can be two quark parton or two gluon partons in the hard interaction. And now that takes us to the subject of generalized parton distributions. So far, any questions? Yes.
Could you explain again why we need to, for the process of plus E minus to anything, why we could set the partons on shell?
Why we could set the parton on shell. So this one?
Yeah.
Do you refer to this cut or this cut?
Second cut.
This one. Okay. So this is a result of factorization. So on this figure, we are not setting the partons on shell. Instead, we produce some partons from the hard interactions, and then these partons, once produced, they trigger a set of collinear activities collected by J1, J2 to Jn. And this can be first factorized in this way, and each is defining a so-called jet function. But for the hard part, the virtuality of the partons are very small. So inside the hard part, we can neglect the parton virtuality and set them on shell. We cannot set them on shell here, but we are able to show that by summing over all possible cuts here, those virtuality cancels. The effect of their virtuality is canceled. So essentially, you forget about all these factors, J1, J2 to Jn, and this soft blob. And that reduces the whole thing into just this hard factor here and hard factor here. And we know that in these two hard factors, we set the partons on shell. And that's what we are doing. It's not that we dictate them on shell. It's that we managed showing that the effect of them not being on shell is power suppressed. And that's given in this power correction term. But the leading effect is that we can put them on shell and literally do the calculation for on-shell partons. And it turns out to be turns out to capture the leading effect of hadron cross sections.
Thank you.
Yes. Yes.
I had a question with the distribution amplitudes.
Yes.
Like slide 15. So I guess I see based on like that diagram that you have for the distribution amplitude, why it's like off diagonal in the integral. Why is it off diagonal like with the pi plus and is like in a vacuum state 0 or?
Why is this a 0 state? So when we convert a diagram into an operator definition, it's literally a Green function definition. So if you look at this quark field here, this is a U quark, so you have a U field, and this is a D bar quark, so you have a D bar field. And the reason why these two are giving us the operators instead of states is because these two lines are off-shell lines. They are complete propagators. So we are having parton fields. And for the pi plus, this is a particle, an on-shell particle. So it's sitting here as an initial state, but we have nothing in the final state. This whole thing is annihilated into two off-shell particles. We no longer have any final state. Or in terms of the scattering amplitude, it's the out state. We have no out state. We only have one in state. And this in state is converted or is annihilated into U and D bar. So there's no other profound reason. It's just how you translate. And the question here?
Thank you.
Okay. So, yes.
Can you explain again for inclusive process?
Yes.
For hadrons, what's the difference between part scattering and so on? Inclusive process.
Sorry. Say it again.
Can you explain again, like for inclusive,
Yes.
like for hadrons, hard part and soft?
This diagram?
Yes.
So this, you can literally think about this as a physical classical picture. You have this parton that comes from this PA, which is the incoming proton state. And this parton enters the hard interaction with this virtual photon. And this hard interaction, it doesn't have to be leading order. It can be arbitrary orders. So it can produce any arbitrary hard collinear parton lines in the final state. And these parton lines, we have color confinement in QCD. Colors cannot isolate, cannot exist in being isolated. So they have to exchange soft gluons with each other to neutralize their colors and confine into hadrons. And that's called hadronization. And we still, to today, we have no good control over the actual mechanism for hadronization. But in terms of the factorization argument, we are more or less making some assumption that, well, you can exchange arbitrary soft gluons, and if I include all possible Feynman diagrams perturbatively, that more or less mimic the actual physical hadronization process. That's an underlying assumption, but a physically sound assumption. So then if you observe a hadron, this hadron has to come from a parton, that's fragments, a collinear parton. So it's associated with this kind of jet factor. And this jet factor has an incoming parton together with some Wilson line, and this gives you the hadron you want to observe along with anything else. And the soft gluons are connecting all these different collinear sectors. So for factorization, we mean that the different collinear factors for this J1 and this JA, they are independent of each other. In other words, the incoming activities from the proton should not affect how the final state parton fragments into the hadron that you observe. And that's why the key part of factorization is to show that soft gluons are canceled. And the soft gluons are canceled because we are able to sum over all the final states. And there are a lot of technicalities associated with this, but physically, that's what it actually does. So soft gluons cancels, and all these unobserved jet blobs are also canceled. And what remains is the two two collinear factors associated with the two hadrons we observe, one in the initial state, one in the final state. And you can imagine if you observe, instead of one hadron, you observe two hadrons, you will have another jet factor, which gives you another fragmentation function in the final state.
That confinement, it doesn't matter inside what happened. The color confinement for gluons, it becomes 0 inside the process. It doesn't matter, like, I didn't see in the final state the same hadrons or it's final state.
Sorry, I don't understand what you're asking.
Like final state is the incoming.
Oh, it doesn't have to be the same. It doesn't have to be the same. Yeah. So the initial state hadron doesn't have to be related to the final state hadron. It can be all arbitrary. And that's actually the key for factorization. They are independent. So you can have a pion, a lambda, anything. Yes. But for exclusive process, they are related to each other. And for exclusive process, is essentially, as we are demonstrating here, this incoming hadron H and diffracted hadron H prime, they are in the same collinear blob denoted by F here. So they are related to each other. And then they are factorized into the new thing that we call generalized parton distribution, or GPD. And what is GPD? It comes from the result. It comes from the factorization argument, and but once factorized, it becomes independent of the process that it's factorized from, and it takes the operator definition by itself. So it's an independent object. It can be studied theoretically just on its own right. And this operator definition is very similar to the operator definition for the PDF we have seen many times before. The only difference is we have different hadron states. We have P and P prime here. Their momenta are different, but for PDF, their momenta are the same. And recall what we learned in quantum mechanics course. Once we are looking at the matrix element of a certain operator, if the states are the same, that's, in other words, called diagonal matrix element. Diagonal matrix element refers to cross-section, something like the probability. But off-diagonal matrix element is something like amplitude, it's transition amplitude. So they are very fundamentally different. So the GPD is defined at amplitude level. And that's why these two fields, to be more strict, these two fields should be time ordered. There should be a time ordered operator in front. And we can understand this better by looking at this amplitude. We have the transition from momentum P to P prime, and you take out two partons from it, and that two partons are given by these two parton fields. And one of them, say this is a quark line, it carries momentum K, and this quark line comes back with momentum K prime. And there is a momentum conservation, as you know. And to describe this, we want to select independent kinematic variables in the simplest form that we want. First, we define the momentum transfer as the delta. Delta is P minus P prime, which is the total momentum given by this parton pair, or P minus P prime, or K minus K prime. And we also define the average of these two hadron states, hadron momenta, P and P prime, as the capital P. And these two are independent momenta and are the only two independent momenta out of these four, p, k, k prime, p prime. And out of this, we define T as the invariant mass of this delta, which is the invariant mass of this parton pair. And we define the similar x variable for the longitudinal momentum fraction carried by these two partons. And this is given by their sum over the p and p prime. And we also define Kc as the relative momentum between these two parton pairs. And this is given in terms of the difference of p and p prime over p plus p prime. And these are all in the plus components. So this may look a little bit complicated, but it's in fact very simple as long as you work this out. The kinematic, that's the kinematics. And in a short summary is we will use three variable x, psi, and t. And the x is similarly to the x in PDF, and psi is the additional momentum difference between the two partons given by the difference of p and p prime. And t captures the invariant mass of this pair. And also for the operator definition we have here, because they are no longer, these two states are no longer diagonal, we cannot simply relate this to a certain function, such as a PDF, but instead, we must decompose this into different structures associated with the spinors for incoming and final state hadron. And those are given by this U and U bar with momenta P and P prime. And the first structure is we have a gamma plus here, and we can also have a structure with this sigma, Dirac sigma matrix. And their coefficients give us the GPDs, H and E, that we want. And these two functions, H and E, are scalar functions. And sometimes we refer to the overall thing as GPD, but mostly we refer to this H and E as GPDs. And this H and E are associated with different hadron spin structures as defined by these spinor structures here. Any questions here? Yes.
Why are the kinematic variables defined specifically in the plus light cone direction?
In terms of plus, first, that's something we like. And the more important reason is when you make factorization argument, it is the plus component that directly enters the hard interaction. So we want to use the plus component. So suppose there's a hard blob on top, what matters in the hard blob will be x and psi. So only the plus component enters the hard interaction. And that's in terms of factorization. And but on the GPD its own, why we use plus is because this makes them boost invariant. Because a plus component has a very clean boost property. If a plus component is only scaled. Yes, so x and psi do not change if you make a longitudinal boost along the z direction. And the reason for using t is because it's Lorentz invariant, right? That's a simple reason. Any other questions? So that's the definition for GPDs. And this can be slightly generalized. We have a gamma plus inserted here to define an unpolarized parton state. And we can also insert an additional gamma 5 to dictate the parton states to be polarized. And that defines two more GPDs that are denoted as H tilde and E tilde. Again, with different spinor structures for the incoming and final state hadrons. And these are just definitions. And if you are confused by the definition details, do not worry because this will not matter so much in the following. And they have some properties. The first property is that they are simply related to the PDFs we have by taking the forward limit. If we take P and P prime to be the same, they reduce to the definition for PDFs. So this H and H tilde will give us the unpolarized quark PDF and polarized quark PDF simply by taking psi and T to 0. And now with a non-zero Xi, the parton momenta will be slightly skewed. So this, in this sense, we call Xi as a skewness. What it means is, suppose here is the horizontal axis is for X, the parton momentum fractions X. And if X is greater than Xi, these two partons will behave as one parton carrying momentum X plus Xi and gets out, and then another quark comes back with momentum X minus Xi. So in net, they transfer a total of 2 Xi momentum fraction out. So this pictures like a quark PDF. And on the other hand, if X is negative in the region between -1 to minus Xi, we have the reversed picture. We have an anti-quark that carries momentum Xi minus X out, and another one comes back with minus Xi minus X. So this is like an anti-quark PDF. And in between, that's something new for GPDs. And in this case, we're having a pair of quark and anti-quark, and they both get out of the proton or any other hadron. And the one carries momentum X plus Xi, the other carries momentum Xi minus X. So in total, they carry a momentum fraction 2 Xi out. So that's the 3 different X regions of the GPDs. And these 3 regions are called 2 DeGlap region and 1 ERBL region, exactly as what I introduced when telling you the factorization properties for GPDs. And any question here? Please feel free to ask me any kinds of question. I know the GPD is kind of a lot if you first say it, because there are a lot of technicalities associated with the definitions, but they are actually not that complicated. It's just once you make the protons off diagonal, you directly introduce a lot of them. And that's exactly the complication of GPDs in reality. You simply have a lot of them with a lot of variables. And why people are interested in GPDs is because it entails some additional information about the partonic structures in the hadrons. And one most intriguing one is called the 3D picture or tomography picture. And that's one of the key important points in the EIC project. And how to understand this, let's think back to introductory QFT course. Say we have the scattering of an electron and proton, elastic scattering. Elastic scattering happens in the way that the electron exchanges a photon with a proton, and the proton and the electron get slightly scattered. So in this case, this blob is formally decomposed into the form factors called F1 and F2. And this is given in the introductory QED section, I believe, in Peskin's book. And with these 2 form factors, F1 and F2, you can take a Fourier transform with respect to T, and that will map you a picture, the electric charge density in the proton or neutron or any other nucleus target. And this gives us something that we can define as the electric charge radius of the proton. And in other words, with the diffraction, you can probe the transverse spatial picture of the proton. And that's what we have in GPD. But GPD has something more. It still has a diffraction. The proton is diffracted with a slight momentum transfer captured by T, similarly to what we have here. But GPD has also a hard interaction given by the same process we have seen several times now. This hard interactions is localized, so it sees the partons. And then that's why we have the parton momentum fraction x here, in addition to what we have here. But we still have a diffraction. So similarly to what we have here, you can take a Fourier transform for GPD with respect to t. Here, I'm taking t to be a transverse momentum squared because we are taking c to 0. And in this case, we are getting also a transverse spatial picture for the parton inside the proton at each momentum fraction x. So this together give us a 3D image of the partons in the proton. So from this, we get something more. We can define, for example, a proton radius in terms of different parton momentum fractions. And that's something more we get compared to here. And this picture was first realized by Burkert in early 2000s. And another physical significance of GPD is that it can be related to something called mechanical form factor. That's another lecture you've heard from Adam. And how do we understand this? We can make the simple analogy with PDFs. We know that PDF has a simple physical understanding that PDF defines the number densities of partons at each momentum fraction. So if we weight the PDF by x and integrate over x, that gives us the total momentum fraction carried by the parton I in the proton. And more formally, because we have the operator definition for the PDFs, by taking the integral of x, we can relate that to the matrix element of this energy momentum tensor. And I will not go into more detail here because you have seen this multiple times in another lecture. And we know the physical meaning. This energy momentum tensor sitting between the proton state maps out the total momentum fraction of the proton carried by the parton flavor I. And we have a momentum sum rule. By summing over the quark and the gluons, you get 1. And similar stories happen for the GPD because we have the same operator. The only difference is that we have different momentum states. So here we have P and P prime. And differently from the PDF case, we need to decompose this into different spinor structures. We have gamma plus, we have I sigma plus delta. And these are exactly what you have seen there in Adam's lecture. This A factor, B factor, and D factor are called the gravitational form factor or mechanical form factors, depending on what you want to call it. And here, what we are getting from the point of view of GPD is on the left-hand side, we have the GPD. And we have managed decomposing this F in terms of H and E. So this H and E are exactly related to these two mechanical form factor A and D and B and D. And we know that by summing over these two, the D form factors get canceled and the remaining A and B will define the angular momentum of the proton. So by integrating over the GPDs H and E weighted by X and integrating over X from -1 to 1 in the limit of T going to 0, we get the angular momentum contributed from the partons, either quark or gluons. And this was first realized by Xiangdong-Ji in 1997. And it's all these beautiful features entailed by the GPDs that we are interested in getting them from experiments. And that leads me to another section, the phenomenology of GPDs. And I think it's a good place to pause here, take whatever questions that you may have.
Any questions? Hey, I had a question on slide 22.
This is with like the GPD being a PDF and a distribution amplitude kind of. Like, why exactly does that change with X? Like, I guess maybe I didn't fully understand this when you explained it the first time. Like, when X is less than C, like between C and minus C, like why does that turn into a distribution amplitude? Like, why do you interpret it as like the two lines are on the left there?
Why do we have this kind of three different regions and pictures? Yes. So it's just, again, there's no much profound reason. It's just the kinematics. You have the formal definition here, and from this you can read out the momentum fraction carried by this k and k prime. One carried x plus psi in the capital P plus, and the other carried x minus psi. And this is in the direction that k goes out and k prime comes back. So now you think if x is greater than psi, then both x plus psi and x minus psi are greater than 0. So we have this picture. One quark goes out, one quark comes back. And now if x is less than psi but greater than minus psi, this x plus psi is positive, but this one is negative. And we don't want to physically think about a quark coming back with a negative momentum, but we want to picture it as an anti-quark going out with a positive momentum. Right? So we just we can reverse this incoming quark as an outgoing anti-quark and reverse its momentum as a sign minus x. And then you think if x is smaller than minus psi, we are sitting in this region, then the psi minus x is still positive, but x plus psi becomes negative. And again, we don't want to think about the quark going out with a negative momentum, but we want to picture this as anti-quark coming back with a positive momentum. That's the anti-quark PDF. And relating to the PDF, why do we have complication here but not there? Because in PDF, we are dealing with cross-section or probability. There is not so much freedom of moving the quark as changing the quark to an anti-quark. A quark is a quark. Anti-quark is an anti-quark. We don't want to talk about a quark with a negative momentum. Right? So, but here we are dealing with amplitude, and negative momentum can be easily transformed into a positive momentum, but with an anti-quark. And also the x is going from -1 to 1, but in PDF, x is going from 0 to 1. Yeah.
Okay, if no questions, then let's thank Zhite.